The solar wind, an unceasing stream of charged particles emitted by our Sun, flows outward in all directions, carving a vast bubble into the surrounding interstellar medium. This bubble, known as the heliosphere, represents the outermost boundary of the Sun's influence, a tenuous but powerful extension of stellar breath. As these solar particles race through space at hundreds of kilometers per second, they push against the galactic winds, those vast flows of plasma and magnetic fields that fill the Milky Way. Far beyond the orbit of Neptune, beyond Pluto, even past the scattered icy remnants of the Kuiper Belt, the solar wind continues its journey. Yet it is not infinite. Eventually, it meets resistance. At a distant frontier known as the termination shock, the solar wind slows down dramatically as it collides with the pressure of the interstellar environment. Beyond this, the heliosheath forms, a turbulent region where solar and galactic forces wrestle in slow motion. At its outermost edge lies the heliopause, the invisible membrane where the pressure of the solar wind balances that of the galaxy itself. It is here, some 120 astronomical units from Earth, that the dominion of the Sun yields to the broader galactic forces. This is not a static boundary. It breathes and fluctuates, expanding during solar maximum, contracting when the Sun quiets. The heliopause is shaped not only by the energy of the Sun, but by the ever-changing density, velocity, and magnetic tension of the galactic winds beyond. As Voyager 1 and 2 pushed through this barrier, humanity glimpsed for the first time the true transition between solar space and interstellar space. They recorded a subtle change in particle composition, a shift in magnetic orientation, a drop in solar wind pressure, all signs that the spacecraft had passed through an invisible, dynamic frontier. And yet, even beyond the heliopause, the Sun's fingerprint lingers. Its magnetic field lines stretch outward, twisted by rotation and carried by the wind like threads in a cosmic loom. Some particles, born in solar flares, continue their long journey, spiraling outward into interstellar space, their energies fading but their origins traceable. In this liminal space between star and galaxy, the contrast becomes profound. The solar wind, once dominant, becomes a whisper against the backdrop of the Milky Way's immense forces. Here, the interstellar medium is not empty, it is laced with charged particles, dust grains, and magnetic currents that flow between stars, shaped by supernovae, black holes, and the collective breath of billions of suns. The Sun, though vast on human scales, becomes just another node in the galactic web, its influence fading into the ambient rhythm of the galaxy. Yet the boundary it creates is not just physical, it is informational. The heliosphere acts as a filter, shielding the inner planets from the full force of galactic cosmic rays. These high-energy particles, accelerated by cataclysmic events across the galaxy, are deflected or slowed by the magnetic turbulence of the solar wind. Without this protective envelope, Earth would be bombarded by radiation levels far higher than those we currently experience. Life, as it exists, has evolved within this shield, a cocoon held together by the outflowing breath of our star. But the question of where the Sun ends and the galaxy begins is not merely one of distance. It is a question of transition, of gradients, of thresholds that shift over time. The heliosphere is not a wall, it is a permeable membrane, a porous veil where particles mix, where energies exchange, where solar and galactic identities blur. The galaxy does not wait politely at the edge, it infiltrates, probes, and occasionally penetrates deep into the solar domain. And the Sun, in turn, sends emissaries, photons, electrons, magnetic ripples, deep into the galactic sea. Recent measurements suggest that the heliopause is not smooth or spherical but distorted, shaped by the uneven pressures of the local interstellar cloud through which our solar system is moving. The Sun plows through this cloud at approximately 26 kilometers per second, creating a bow wave, possibly even a bow shock, much like a boat moving through water. Magnetic fields compress and bend in complex geometries, and charged particles spiral along field lines that shift with every solar cycle. The shape of this outer frontier resembles more a windswept flame than a bubble, fluttering and warping under galactic pressure. Embedded within this boundary are clues to processes that govern not just our Sun, but all stellar systems. The solar wind is a form of stellar feedback, and its interaction with the galaxy mirrors larger astrophysical phenomena. Massive stars generate winds 1,000 times stronger, shaping entire star-forming regions, carving cavities in molecular clouds, and triggering the birth of new generations of stars. On even greater scales, supermassive black holes at the centers of galaxies unleash relativistic jets that stretch for hundreds of thousands of light-years, creating galaxy-wide winds that regulate the growth of stellar populations. What the Sun does on a small scale, galaxies do on a grand one. And yet, the physics is eerily similar. Plasma flows obey the same magnetohydrodynamic equations. Shocks form when fast winds encounter dense regions. Reconnection events, where tangled magnetic fields snap and reform, release bursts of energy both near the solar corona and in vast galactic outflows. The Sun is a microcosm of cosmic forces, and its wind a laboratory in motion, accessible to us through spacecraft and instruments delicately tuned to the faintest whispers of charged particles. Perhaps most mysterious is the role of cosmic rays, those ultra-energetic particles that race through the galaxy at nearly the speed of light. The heliosphere slows their approach, modulates their intensity, and in doing so, creates a variable radiation environment within the solar system. Understanding this modulation is not just a matter of protecting astronauts, it is a window into the structure of space itself. Each fluctuation in cosmic ray flux carries information about distant supernovae, magnetic storms in the galaxy, and the dynamism of the heliospheric shield. As we learn more, the question deepens: is the heliosphere unique, or is it typical of stars like the Sun? Are there solar systems whose winds punch further into the galaxy, or others whose protective bubbles have collapsed under stellar inactivity or galactic storms? What would a planetary system look like without a solar wind to shield it? Could life arise in such an exposed environment, or would it be extinguished before it could ever begin? Even now, probes like IBEX and the upcoming IMAP mission are mapping the edges of this frontier, detecting neutral atoms born from collisions at the Sun-galaxy interface. Voyager 1 and 2, now sailing through interstellar space, continue to send back data from the other side, whispers from a region no human-made object had ever entered. And what they find is not silence, but structure. A foamy, magnetized, turbulent sea. A place of boundary-crossing particles, hybrid physics, and the lingering breath of stars. The structure of the heliosphere is governed by the complex interplay between solar and interstellar magnetic fields, both of which are frozen into their respective plasma flows. As the supersonic solar wind approaches the termination shock, it begins to decelerate due to the rising pressure of the local interstellar medium, LSM. At this shock, which forms at approximately 75 to 95 Australian dollars depending on solar activity, the solar wind transitions from supersonic to subsonic, and its thermal and magnetic properties shift dramatically. Post-shock, in the heliosheath, the flow becomes turbulent and compressed, creating a region where kinetic, thermal, and magnetic energies are converted and redistributed. The local interstellar medium itself is a partially ionized plasma, composed of hydrogen atoms, helium, cosmic dust, and galactic magnetic fields with an average strength of about 3 to 5 microgauss. When neutral hydrogen atoms from the LSM drift into the heliosphere, they interact with the solar wind through charge exchange, one of the most critical processes at this boundary. In this interaction, a fast-moving solar wind proton captures an electron from a slow neutral hydrogen atom, creating a neutral solar wind atom and a slow-moving ion. These energetic neutral atoms, ENAs, then escape and can be detected by instruments like IBEX, which builds a global map of the heliosphere from these signals. This charge exchange process is not just a peripheral interaction, it is a dominant mechanism in the energy and momentum transfer at the heliopause. The resulting ENA maps have revealed that the heliosphere might not be comet-shaped, as traditionally imagined, but rather more spherical or even bubble-like in certain models. Some researchers propose a croissant shape, where the heliospheric tail splits into two lobes due to the influence of the interstellar magnetic field, an idea supported by multi-year measurements of ENA fluxes and magnetic vector orientation from Voyager data. In addition to ENAs, the heliosphere is also a modulator of galactic cosmic rays, GCRs. These high-energy particles, originating from extragalactic sources and from within the Milky Way itself, primarily supernova remnants, experience diffusion, convection, and adiabatic deceleration as they traverse the heliosheath. The Parker transport equation governs their propagation, accounting for solar wind velocity, magnetic turbulence, drift effects, and energy loss mechanisms. The intensity of cosmic rays reaching the inner solar system is inversely correlated with solar activity. During solar maximum, a stronger solar magnetic field and faster wind create a more effective barrier, while during solar minimum, cosmic ray intensity increases significantly. On galactic scales, analogous processes occur on orders of magnitude greater. Galaxies with high rates of star formation often exhibit galactic superwinds, massive outflows of ionized and molecular gas driven by collective supernova explosions and stellar winds. These flows can escape the gravitational potential of their host galaxy, enriching the intergalactic medium with metals, disturbing surrounding halos, and even triggering star formation in satellite systems. The physics of these outflows parallels that of the solar wind, but with additional complexities such as radiation pressure, shock heating, and multiphase turbulence. The study of the heliosphere thus provides a testbed for understanding more violent and energetic feedback in starburst galaxies and active galactic nuclei, AGN. In both cases, stellar and galactic, the outflows are not isolated. They carry signatures of the environment from which they emerge, encoding information about magnetic topology, energy injection rates, and the geometry of the surrounding medium. In turn, they reshape their environment, creating feedback loops that regulate growth, chemistry, and structural evolution. One of the most profound insights emerging from heliospheric and astrophysical studies is the universality of plasma behavior across scales. Whether in the tenuous outskirts of the solar system or in the heart of an active galactic nucleus, the interplay of charged particles and magnetic fields follows the same fundamental laws, magnetohydrodynamics, MHD. The heliosphere becomes not just a boundary, but a miniature laboratory where these laws can be observed directly, in ways that complement and calibrate large-scale cosmological models. Magnetic reconnection, for example, a process where magnetic field lines break and reconnect, releasing enormous amounts of energy, is observed both in the solar corona and in galactic jets. In the heliosheath, reconnection may occur between the heliospheric and interstellar magnetic fields, facilitating the escape of energetic particles and the entry of cosmic rays. Such reconnection events contribute to particle acceleration, turbulence, and changes in the global structure of the heliosphere. Observations from Voyager have hinted at these dynamics, as sudden changes in plasma density and magnetic orientation suggest localized reconnection zones far beyond the orbit of Pluto. Turbulence, too, plays a critical role. The heliosheath is not a smooth layer but a chaotic environment of eddies, waves, and fluctuations, an astrophysical ocean in miniature. Models suggest that this turbulence is driven by instabilities at the termination shock, modulated by solar cycles and the non-uniform flow of the interstellar medium. Turbulence enhances mixing, diffuses cosmic rays, and can amplify magnetic fields through dynamo-like processes. On galactic scales, turbulence shapes star-forming clouds, redistributes angular momentum, and supports or suppresses star formation depending on its intensity and scale. Recent numerical simulations have begun to bridge the scales between the heliosphere and galactic outflows. Using adaptive mesh refinement and hybrid particle-in-cell methods, researchers simulate the transition from supersonic to subsonic flow, shock formation, and the behavior of neutral atoms under ionizing radiation. These models have revealed surprising phenomena: draped magnetic fields around the heliopause, Kelvin, Helmholtz instabilities on its surface, and regions of enhanced pressure where the solar and galactic environments intertwine. The heliosphere also acts as a filter for interstellar dust. Micron-sized grains entering from the LSM are deflected or slowed by the solar magnetic field and radiation pressure. The distribution and trajectory of these grains provide information about the galactic magnetic field's orientation and the grain's charge-to-mass ratio. Such measurements, combined with infrared observations and spacecraft detections, allow astrophysicists to reconstruct the composition and origin of dust from distant regions of the Milky Way, some of which may be remnants of ancient supernovae or fragments of interstellar comets. As we look outward, the Sun's influence begins to vanish, but not immediately. Magnetic sectors continue to ripple through the local interstellar plasma, and relics of past solar activity, like coronal mass ejections, propagate into deep space. The so-called fossil fields, embedded in solar ejecta, may persist for decades or centuries, slowly mixing with the galactic medium. These remnants leave behind complex plasma signatures, traceable by future probes, offering a time-stamped archive of solar activity preserved in the cold quiet of interstellar space. And while Voyager 1 and 2 continue their silent traverse into this new realm, future missions, such as the interstellar probe concept proposed by NASA, aim to go further and faster. These missions seek to escape not just the Sun's plasma boundary but the entire gravitational grasp of the solar system, journeying into pristine interstellar environments untouched by the solar wind. With such data, we may finally answer questions that span from the nature of our Sun's past to the conditions surrounding nascent planetary systems across the galaxy. These future interstellar missions aim not only to map the density, composition, and temperature of the local interstellar medium with unprecedented precision, but also to probe the galactic magnetic field, something still largely inferred indirectly from polarized starlight and synchrotron emissions. By directly measuring the vector orientation and strength of magnetic fields beyond the heliopause, such missions could unlock a deeper understanding of how the Milky Way's magnetism threads through space, guiding the motion of cosmic rays, shaping interstellar clouds, and influencing the birthplaces of stars. Furthermore, these spacecraft would provide critical data on the ionization state and elemental abundances of the interstellar plasma. Are the atoms out there primarily hydrogen, or is there a trace of heavier elements, carbon, oxygen, iron, blown outward by ancient supernovae and stellar winds? How much of this material is locked in dust grains, and how much floats freely in gas form? These questions are essential not only for galactic evolution models but for understanding the chemical pathways that may seed life throughout the galaxy. One of the more subtle goals of such missions is to understand the interaction between galactic cosmic rays and the interstellar environment itself. Cosmic rays are not passive passengers through space. Their movement can generate waves in the interstellar plasma, modulate magnetic fields, and even contribute to the heating of diffuse gas. By observing how these particles behave just outside the heliosphere, unmodulated by the solar wind's shielding, scientists could test long-standing theories of particle diffusion, acceleration, and energy loss in galactic environments. And what of the Sun's motion itself? As it orbits the galactic center at around 230 kilometers per second, it plunges through different regions of the galaxy, clouds of cold neutral gas, hot ionized voids, and turbulent filaments shaped by long-dead stars. The Sun's past path may have carried it through supernova remnants, and its future may lead into denser molecular regions. Each crossing could reshape the heliosphere, shrink or expand the protective bubble, and radically alter the flux of cosmic rays reaching Earth. Some studies even suggest that past ice ages or extinction events might correlate with such galactic transitions, cosmic weather on million-year scales. On even longer timescales, the heliosphere is not stable. As the Sun evolves, it will eventually swell into a red giant, shedding its outer layers and extinguishing the solar wind. The heliosphere will collapse, exposing any remaining planets to the full intensity of the interstellar environment. Over time, only a white dwarf will remain, drifting through the galaxy in silence. The legacy of the solar wind, once a mighty force carving a protective shell around its children, will vanish, its boundary erased, its memory fading into the interstellar night. Yet the imprint it leaves, on Voyager, on interstellar atoms, on magnetic echoes, may persist. In the same way that we now detect supernovae from stars that died millions of years ago, future observers might detect traces of extinct heliospheres, faint plasma bubbles, dust shadows, and magnetic scars drifting between the stars. The solar wind, though born from a single star, participates in a much grander pattern, a galactic symphony of breath and boundary, of expansion and dissolution. Through the study of this invisible wind, we touch not just the outer limits of our solar system, but the deep mechanisms that structure galaxies, define cosmic space, and shape the conditions for life. The Sun's breath is a whisper, but in the vast quiet of space, that whisper echoes endlessly. Understanding the full extent of the solar wind's legacy also invites a broader question: how typical is our heliosphere among the billions of stellar systems in the Milky Way? Every star with a sustained outflow, whether a gentle breeze like the solar wind or a ferocious stellar gale, produces its own astrosphere, a plasma envelope that interacts with the surrounding interstellar medium. For massive, hot stars, this bubble can stretch dozens of light-years, sweeping up material and compressing it into dense shells that may become the seeds of future star formation. For cooler red dwarfs, the outflows are weaker and more chaotic, but still capable of sculpting space on small scales. Astrospheres are not just passive structures, they are active zones of chemical and radiative transformation. Within these envelopes, particles are accelerated, dust is charged, and radiation fields are reshaped. The boundaries of these spheres are likely rich in shock chemistry and magnetic turbulence, potentially fostering exotic molecular pathways or facilitating the breakdown of interstellar ices. In this sense, the heliosphere may not just be a shield, it may be a crucible, processing the raw ingredients of interstellar space into something new, something complex. This has profound implications for planetary habitability. Planets orbiting stars without a robust wind may be more vulnerable to the galactic environment, subject to higher cosmic ray fluxes, greater atmospheric erosion, and stronger magnetic interactions with the interstellar field. Conversely, an overly strong stellar wind might strip atmospheres away or bathe planets in intense radiation. The heliosphere thus becomes a kind of Goldilocks zone, not too strong, not too weak, a balanced cocoon that may have enabled Earth's biosphere to emerge and persist. Some recent models even suggest that galactic magnetic fields could interact with stellar astrospheres to focus or funnel cosmic rays into specific regions, creating zones of higher or lower radiation exposure. This could mean that even within the same solar system, outer planets might experience different levels of cosmic bombardment depending on their position within the heliospheric architecture. It raises the possibility that magnetic field topology, not just planetary distance from the host star, might play a crucial role in long-term planetary habitability. Observations of other astrospheres, particularly around young stars, provide further insight. Infrared data from telescopes like Spitzer and Herschel have revealed bow shocks around fast-moving stars, compressed arcs of heated dust and gas that trace the interaction of stellar winds with the local medium. These structures are thought to be analogous to the Sun's own motion through the galaxy, suggesting that the heliosphere may have exhibited radically different shapes and behaviors in the past. By mapping the diversity of stellar wind environments, we begin to place our own solar history within a broader cosmic context. Even within the Milky Way, regions differ dramatically in interstellar density, temperature, ionization, and magnetic field strength. As the Sun moves along its 230 million-year galactic orbit, it weaves in and out of these regions like a swimmer crossing oceanic currents. At times it may enter hot, diffuse voids, where the heliosphere expands and the solar wind flows freely. At other times, it may plunge into cold, dense clouds, compressing the heliosphere and perhaps even altering the delivery of interstellar material into the inner solar system. These transitions may not just reshape space, they may leave fingerprints in the geological and climatic history of Earth and its neighbors. Each crossing, each boundary, each shift in magnetic orientation represents a new chapter in the long interplay between a single star and the galactic tides that surround it. The heliosphere is not a closed structure, it is a living frontier, dynamic and responsive, shaped by forces both local and cosmological. And in studying it, we are not merely tracing the winds of our Sun, we are listening to a deeper cosmic dialogue, one that connects particles and fields across light years, one that writes the invisible script of stellar evolution, planetary survival, and the architecture of the galaxy itself. The heliosphere's role as an intermediary between solar and galactic forces also extends into the domain of dust, ices, and the chemistry of prebiotic molecules. As interstellar dust grains drift toward the Sun, they enter this magnetic shield and experience deceleration, deflection, and sputtering from solar radiation and charged particles. But despite this gauntlet, some grains penetrate deep into the solar system, bearing isotopic signatures and complex organic compounds formed in ancient stellar nurseries or shock fronts of long-dead stars. These grains are messengers, carrying the chemical memory of the galaxy into the heart of our planetary system. Indeed, some of the very atoms now circulating in Earth's oceans and atmosphere may have once traveled through interstellar space, briefly touched the boundary of the heliosphere, and entered the gravitational pull of our Sun. This exchange of material is subtle but continuous, and it speaks to a fundamental truth: even the most isolated planetary systems are never truly closed. They are porous, permeable, connected to the broader chemical evolution of the galaxy through winds, dust, and cosmic rays. This has led to an emerging field of heliospheric astrobiology, where scientists explore how cosmic environments influence the conditions for life. It is no longer enough to consider planetary habitability solely based on distance from a star. Instead, the full radiation environment must be modeled: how the heliosphere deflects or channels galactic cosmic rays, how solar storms might affect atmospheric retention, how magnetic reconnection events could trigger photochemical reactions in upper atmospheres. Every molecule of life is shaped not just by planetary chemistry, but by the invisible war between stellar and galactic winds. Cosmic rays, for example, can induce secondary particle showers in planetary atmospheres, altering chemical bonds and even generating rare isotopes like carbon-14. On early Earth, these high-energy interactions may have played a role in creating nitrates, hydrogen cyanide, and other molecules essential for the origin of life. In this way, the balance between solar wind shielding and cosmic ray penetration becomes a cosmic tuning fork, setting the stage for biochemistry before biology even begins. In exoplanetary systems, the stakes are even higher. For worlds orbiting red dwarfs, known for their intense flares but weak winds, the lack of a strong astrospheric shield could mean relentless exposure to galactic radiation. On the other hand, massive stars with powerful stellar winds might produce vast astrospheres but sterilize nearby planets with ionizing radiation. Only a narrow band of stellar wind characteristics may strike the right balance, creating a stable, shielded environment while avoiding atmospheric erosion or magnetic stripping. Understanding our heliosphere structure and evolution offers a rare template for identifying such conditions elsewhere. From this perspective, the heliosphere becomes more than just a structure, it is an evolutionary factor. Its behavior over millions of years may have modulated the rate of mutations via cosmic ray flux, altered climate through solar modulation, and even influenced extinction and radiation-driven adaptation cycles. When placed in geological context, spikes in cosmic ray flux can be correlated with magnetic reversals, climate anomalies, and mass extinctions. These are not random events, they are echoes of the galactic environment filtering through the dynamic lens of the heliosphere. As our instruments improve, we begin to see the heliosphere not as a boundary at all, but as a dynamic interface, an adaptive membrane between solar identity and galactic reality. Every Voyager signal, every ENA detection, every solar storm recorded by Parker or Solar Orbiter adds a new pixel to this invisible map. A map not of places, but of forces. Not of locations, but of interactions. And through it, we glimpse the choreography of matter, energy, and time on the scale of both stars and galaxies. In this ongoing conversation between the Sun and the Milky Way, one of the most revealing aspects is the alignment, or misalignment, between their respective magnetic fields. The solar magnetic field, carried outward by the solar wind, forms a spiral structure known as the Parker spiral, shaped by the rotation of the Sun. As it extends into space, this spiral interacts with the galactic magnetic field, which is oriented in a completely different direction, shaped by the shear and rotation of the galaxy itself. At the heliopause, where these fields meet, a complex magnetic sheath forms, a turbulent, twisted region where magnetic reconnection can occur on a massive scale. This region not only accelerates particles but acts as a filter, selecting which cosmic rays may pass through and which are deflected. It is an invisible battlefield of field lines and charged flows, where the geometry of space itself becomes an active participant in the physics of the boundary. Surprisingly, data from Voyager 1 and 2 revealed that the magnetic field direction did not change dramatically across the heliopause, as was expected. This finding challenged previous models and suggests that the interaction zone may be broader and more integrated than we imagined. Perhaps the solar and galactic fields are more entangled, woven into a shared structure that resists clean separation. This entanglement has significant implications. It could mean that our solar system is more exposed to galactic radiation during certain epochs, depending on the orientation of these fields and the Sun's passage through different regions of the galaxy. In fact, paleoclimate records and radionuclide data from ice cores and ocean sediments show periodic increases in cosmogenic isotopes like beryllium-10 and carbon-14. These anomalies correspond to episodes of weakened heliospheric shielding, possibly due to grand solar minima, magnetic field reversals, or traversals through interstellar clouds. Each spike tells a story, not just of solar variability, but of galactic weather patterns rippling into the Earth's biosphere. Galactic weather, while poetic, is not a metaphor. It includes real changes in the pressure, density, and composition of the interstellar medium, driven by supernova shock waves, density waves within the spiral arms, and even the gravitational pull of dark matter substructures. As the solar system drifts through this landscape, the heliosphere expands and contracts like a lung, breathing in the galaxy's evolving environment. Even the notion of a stable interstellar medium is being re-evaluated. The Sun currently resides in the local interstellar cloud, a warm, low-density pocket of gas and dust, but it is approaching the boundary of a new region, the G cloud. If the solar system enters a denser or more magnetized zone, the heliosphere could shrink dramatically, exposing the planets to greater fluxes of cosmic radiation and interstellar particles. Simulations suggest that in such cases, the heliopause could contract to within $50 placing even the outer planets like Uranus and Neptune partially outside the Sun's magnetic protection. In a broader astrophysical context, this interaction is not unique to the Sun. Every star with a wind must engage in this same negotiation with its galactic environment. And as we discover more exoplanets, particularly those orbiting stars in dense clusters or in regions of high supernova activity, we must ask, what kind of heliospheres protect, or fail to protect, these distant worlds? Could the architecture of a heliosphere dictate whether a planet retains an atmosphere? Could variations in stellar wind strength explain why some planets remain habitable while others are scorched or frozen? The answers lie at the intersection of stellar astrophysics, plasma physics, and galactic dynamics, a truly interdisciplinary frontier. In that sense, the study of the heliosphere is no longer a niche domain. It is central to understanding the cosmic context of planetary systems, the environmental pressures that shape evolution, and the subtle connections between local astrophysical phenomena and the vast machinery of galaxies. The solar wind, born in the crucible of the sun, carries more than heat and charged particles, it carries information. About us. About the galaxy. About the delicate tension that holds together our corner of the universe. And at the heart of this tension lies an even deeper mystery: how does the sun's wind evolve over stellar time? The solar wind we measure today is the product of a middle-aged star, stable and relatively quiet in its magnetic temperament. But in its youth, the sun was far more volatile. Studies of young solar analogs, G-type stars just a few 100 million years old, reveal solar winds that are not merely stronger but often hundreds of times more intense, driven by extreme magnetic activity and frequent stellar flares. This T-Tauri wind phase, as it's known, may have dramatically sculpted the early solar system. In that era, the heliosphere would have been vast and violent, a pulsating shell of plasma pushing back against the dense and chaotic interstellar surroundings of the young Milky Way. Such winds likely stripped atmospheres from the first generation of rocky planets or stunted the growth of protogas giants by sweeping away volatile material. Conversely, they may have also protected the inner system from the worst of the galactic bombardment, allowing fragile molecules to survive in shaded niches, crucial in the formation of complex organics. The effects of this early heliosphere would still be imprinted in the isotopic ratios found in meteorites, in noble gases trapped in ancient zircons, and perhaps even in the deep structures of planetary cores. A more intense solar wind implies more robust magnetic interactions with planetary fields, creating auroras and magnetospheric storms that would have dwarfed anything seen today. In those chaotic eons, the interplay between solar output and galactic conditions may have dictated which planets cooled fast enough to form crusts, which retained their atmospheres, and which were forever altered by the violent plasma seas. Over billions of years, as the sun aged and quieted, the heliosphere stabilized. Its current structure, mapped in part by Voyager, IBEX, and soon IMAP, represents a kind of temporary equilibrium. But it is fleeting. Stellar evolution ensures that this balance will not last. In the distant future, as the sun exhausts its hydrogen fuel and expands into a red giant, the solar wind will increase once again, this time as a slow, dense outflow of mass loss. This dying breath will erode the boundaries of the heliosphere, flooding the surrounding interstellar space with heavy elements, carbon, oxygen, nitrogen, and silicon, forged in the core over billions of years. The heliosphere will cease to exist as we know it, dissolving into the ambient galactic medium. The solar system's magnetic shield will collapse, and the sun will end its life not with a bang, but with a final dispersal, a planetary nebula expanding into the galaxy, like so many that came before it. And then, in silence, a white dwarf will remain, a ghost of fusion, surrounded by debris, perhaps a few icy moons or asteroids clinging to gravity's last grip. No more wind. No more shielding. Just echoes in plasma and dust. But the story does not end there. Those ejected elements will become part of the next cycle. Galactic winds will carry them into molecular clouds, supernova shocks will compress them into star-forming regions, and gravity will sculpt them into new suns, new heliospheres, and perhaps, once more, life-bearing planets. Thus, the heliosphere is more than a protective shield. It is a participant in cosmic ecology. It filters, modulates, preserves, and eventually contributes. It is both a wall and a bridge, defending its system from chaos, and then offering its ashes back to the galaxy that gave it birth. And in every solar wind particle, in every ENA detection, in every Voyager transmission from the edge of interstellar space, we are reading a piece of that story, an unfolding dialogue between a star and the galaxy, between a local breeze and the vast currents of the cosmos. A dialogue we are just beginning to understand. As we continue deciphering this cosmic dialogue, new instruments are poised to radically transform our understanding of the heliosphere's structure, evolution, and role in galactic processes. The Interstellar Mapping and Acceleration Probe, IMAP, set for launch in the coming years, will refine our global maps of the heliosphere by detecting energetic neutral atoms, ENAs, with unprecedented sensitivity. These atoms, born from charge exchange between solar wind ions and interstellar neutrals, carry with them precise information about the pressure, composition, and flow dynamics of regions far beyond the reach of traditional probes. By capturing these ENAs and reconstructing their trajectories, IMAP will allow researchers to visualize the heliosphere in full 3D for the first time, revealing its true geometry, asymmetries, and possibly even its time variability on short and long timescales. Will it confirm the twin-lobed, croissant model predicted by recent simulations? Or will it uncover previously unseen structures, like folded current sheets, tail shocks, or plasma chimneys where energy escapes into interstellar space? Such observations are more than cartographic, they're diagnostic. They will allow physicists to refine models of MHD turbulence at the solar galactic boundary, to test predictions of how cosmic rays drift through magnetic irregularities, and to evaluate how instabilities, like Rayleigh-Taylor or Kelvin-Helmholtz modes, develop and propagate along the heliospheric shell. These instabilities, long theorized but never directly imaged, could allow interstellar material to leak inward or solar particles to bleed outward, blending the two domains in ways far more complex than previously assumed. Simultaneously, Earth-based and near-Earth instruments, like AMS-02 on the International Space Station and the IceCube Neutrino Observatory at the South Pole, are detecting charged and neutral particles from across the galaxy, some of which have passed through the heliosphere, others which have been deflected or transformed by it. Their energy spectra, composition, and arrival directions provide indirect but powerful insights into how our local plasma environment reshapes cosmic information. Every cosmic ray is a probe, and every deviation in its path is a fingerprint of the heliosphere's influence. In the meantime, theorists and computational physicists continue to push the boundaries of modeling. New simulations that combine magnetohydrodynamics with kinetic particle tracking now account for charge exchange, turbulence, multi-ion plasmas, and anisotropic pressure gradients. These models can simulate how a single interstellar shock might compress the heliosphere, or how a coronal mass ejection might ripple outward to the heliopause and trigger magnetic reconnection on a vast scale. Some models even explore the feedback effects of heliospheric activity on the surrounding interstellar cloud, suggesting that the solar system is not just passively moving through space, but actively altering its local galactic environment over time. This idea, that stars sculpt their surroundings on parsec scales, has profound implications for galactic ecology. In dense star-forming regions, overlapping heliospheres may interact, merge, or collide, creating nested bubbles of plasma that become observable as superbubbles or radio-emitting filaments. In some regions, these overlapping winds could trigger the compression of molecular gas, initiating new waves of star formation. In others, they could evacuate gas, halting stellar birth for millions of years. The heliosphere, once thought to be a local and largely self-contained structure, now emerges as a fundamental unit of feedback within the larger galactic metabolism. And as we refine our understanding of how stellar systems like ours engage with the galaxy, we open new doors in the search for life beyond Earth. Could heliosphere-like structures be detected around other stars, indirectly, by observing the modulation of their X-ray or UV emissions? Could we one day infer the shape and strength of an exoplanet's astrosphere, and use that to assess its radiation environment, habitability, or magnetic shielding? Such questions are no longer hypothetical. They are becoming part of an emerging field, interstellar space weather. In the future, models of exoplanet habitability will likely include not only stellar luminosity and orbital parameters, but also wind pressure, magnetospheric geometry, and cosmic ray flux modulated by distant heliospheres. We may begin to classify stars not just by spectral type, but by their ability to create protective plasma environments, classifying them by the architecture of their influence. Thus, the study of the heliosphere is evolving into something larger. It is a new lens on cosmic structure, linking particle physics with galactic dynamics, planetary science with cosmochemistry. In every solar gust, in every charged ion, in every ENA that drifts across space, we see a microcosm of the universal struggle: containment versus exchange, order versus turbulence, identity versus integration. And we, orbiting quietly within this glowing shell, are not merely passive observers. We are the first to recognize it, to name it, to trace its edges, not from the outside, but from within. That fact alone transforms the heliosphere from a plasma boundary into something else entirely, a threshold of perception, the place where a star begins to understand its place in the galaxy. As our observational reach extends further into interstellar space, it becomes increasingly clear that the heliosphere is not a mere buffer, it is an active interface of galactic consequence. Its very existence modulates not only particle flows but the propagation of electromagnetic waves across large distances. Even light, when passing through regions of turbulent plasma, can be subtly scattered or polarized, meaning that heliospheric structure may leave imprints on the signals we receive from distant quasars and pulsars. These imprints, though faint, are detectable, and their patterns can be used to infer the distribution and motion of charged particles far beyond the solar system. The heliosphere's contribution to the galactic ecosystem also includes its role in redistributing heavy elements. The solar wind carries with it a continual outflow of ions and isotopes, some of which were synthesized during earlier epochs of solar fusion or in primordial nucleosynthesis. Over the lifetime of the Sun, this material accumulates in the interstellar medium, enriching it atom by atom. On long timescales, this gentle wind becomes a source of galactic metallicity, an agent in the slow chemical evolution of our spiral arm. More dramatically, when the Sun enters its final stages of evolution and begins to shed its outer envelope, the solar wind will transition into a planetary nebula wind, a thick, slow-moving expulsion of gas enriched with elements like carbon, nitrogen, and oxygen. These elements, released in large quantities, will not simply drift into silence, they will be swept up by galactic currents, pulled into the gravitational wells of future star-forming clouds, and eventually recycled into new stars and planetary systems. Thus, the final act of our Sun will be a contribution, a final transmission of chemical identity into the next generation of worlds. In this way, the heliosphere is both cradle and crucible. It protects, shapes, filters, accelerates, and ultimately returns. And this cyclical role connects it to the larger cosmic processes of entropy, energy distribution, and structural formation. Where once it was viewed merely as a defensive shell, an accidental byproduct of stellar outflow, we now see it as a coherent structure participating in galactic thermodynamics and cosmic feedback. Advanced heliospheric simulations even suggest that the shape and evolution of these plasma bubbles might contribute to large-scale magnetic coherence across spiral arms. As multiple heliospheres interact, merge, and decay, they create anisotropies in the magnetic field distribution of the galaxy. These variations, in turn, influence the directionality of cosmic rays and possibly affect galactic-scale magnetic reversals or flips, phenomena still poorly understood but evidently tied to the cumulative behavior of individual stellar systems. Moreover, heliospheres may act as temporary reservoirs for antimatter particles. Cosmic ray detectors aboard satellites have occasionally picked up anomalous signatures, positrons and antiprotons in greater numbers than expected. Some of these may be traced to pulsars or exotic decay processes, but others could be due to interactions within heliospheric or astrospheric boundaries, where high-energy collisions trigger pair production or asymmetric scattering. The physics here verges on the edge of fundamental research, hinting at links between local plasma behavior and cosmological asymmetries in matter distribution. And as the Sun continues to move through the Milky Way's gravitational potential, it may one day exit the local bubble entirely, a region thought to have been carved out by ancient supernovae and filled with hot, rarefied gas. The transition into a denser or colder region would immediately alter the balance of forces at the heliosphere's edge, potentially compressing the boundary inward and triggering a cascade of new phenomena, stronger charge exchange, higher cosmic ray fluxes, or even a dramatic shift in the structure of the heliotail, the turbulent wake that trails the Sun like a cosmic fingerprint through the galaxy. The heliotail itself remains one of the least understood features of our solar system. It likely stretches for hundreds, possibly thousands, of astronomical units, a twisting ribbon of slow solar wind, magnetic turbulence, and interstellar matter, braided and swept into filamentary shapes by the Sun's motion. Studying this region may be key to understanding not only how the Sun's past activity has been preserved in plasma structures, but how similar tails from other stars might overlap, interact, and seed galactic structures on massive scales. Ultimately, the heliosphere is not just a local phenomenon. It is a dynamic, evolving expression of stellar identity, an electromagnetic portrait painted across the interstellar canvas. Its behavior teaches us not only about our Sun, but about stars in general, how they breathe, how they defend, how they connect. Through it, we see the invisible architecture of space become visible. And within that architecture, we find not separation from the galaxy, but continuity. A seamless plasma membrane across which energy, information, and matter circulate. To study the heliosphere is to study the self-awareness of a star, extended into space. It is to witness the fingerprint of a singular fusion engine engaging with the tidal forces of the cosmos. And in that engagement, something remarkable happens. Boundaries do not isolate, they transmit. They do not shield, they shape. And in shaping, they reveal that every wind is part of a larger storm, every breath part of a collective rhythm, and every star, through its heliosphere, a voice in the galactic chorus. As we follow this stellar voice into the deeper currents of interstellar space, it becomes clear that the heliosphere is not merely the outermost expression of solar activity, it is a living, evolving archive of solar history. Every layer of the heliosphere is encoded with the memory of past coronal mass ejections, solar maximums, magnetic field reversals, and flux variations. These structures do not vanish, they propagate outward at different speeds, forming concentric plasma shells and fossilized shock fronts. They move like time capsules, drifting into the heliotail, carrying imprints of the Sun's changing character through time. One of the most intriguing areas of research focuses on the stratification of these ancient solar events in the far heliosphere. By detecting subtle variations in plasma density, magnetic turbulence, or ENA fluxes at extreme distances, we may eventually reconstruct a chronological record of the Sun's behavior stretching back thousands of years. This would be nothing less than a heliophysical stratigraphy, a layered map of solar evolution written into space itself. But the heliosphere is also a messenger from the galaxy. Interstellar particles that cross the heliopause carry information from distant regions of the Milky Way, some hundreds of light-years away. These neutral atoms, unaffected by magnetic fields, travel vast distances and deliver pristine data about the temperature, composition, and flow direction of the local interstellar medium. As they are intercepted and ionized inside the heliosphere, they offer us a direct sample of the galaxy's present state, its dynamic structure, its movement, and its subtle gradients. These interstellar inputs are not just passive, they interact with solar particles, create hybrid plasmas, and initiate chemical reactions that would not occur in the unfiltered vacuum of space. This constant interplay between incoming and outgoing streams defines the outermost regions of the heliosphere, where the Sun's identity is gradually diluted into the galactic whole. In this mixing zone, the physics of two regimes, the solar and the interstellar, merge into a plasma state that cannot be described by either alone. It is here, in this frontier region, that nature becomes most creative. Recent proposals even suggest that such boundary zones could serve as natural accelerators for cosmic rays. The complex magnetic geometries, shock fronts, and reconnection layers present at the heliopause and within the heliotail could re-energize charged particles, giving rise to anomalous cosmic rays, particles with energies just beyond what traditional solar processes can explain. These particles, once detected, blur the line between local and galactic physics. Are they born of our Sun's boundary, or merely passing through it? As more sophisticated detectors are launched, whether in deep space or at high-altitude balloon observatories on Earth, we are likely to find increasing evidence that the heliosphere is a participant in particle acceleration at multiple scales. This would place our local star not only as a protector, but as a cosmic sculptor, adding structure and energy to the very medium through which galactic signals travel. And beyond even the heliotail lies the possibility of direct contact with other stellar winds. In crowded regions of the galaxy, stellar nurseries, clusters, and the dense core, heliospheres may overlap or collide, creating vast interacting plasma zones where information and material flow freely between stars. These regions could serve as pathways for molecular transport, magnetospheric exchanges, and even planetary debris dispersal. The boundary between stellar systems, once thought to be sharp and impassable, becomes a gradient of diffusion, an interstellar commons. In this vision, the heliosphere is no longer a solitary shell, it is part of a network. A network of stellar breath, woven into the galaxy like filaments in a vast magnetic web. Through this web, not only do particles move, but so does structure, pressure, turbulence, and potentially even signals, encoded in fields, imprinted in waves, traveling between stars over millions of years. In this sense, the galaxy is not a vacuum, it is a resonating chamber, and the heliospheres are its harmonic nodes. Ultimately, this redefines how we think of space. What was once considered empty is now known to be structured, filled with invisible boundaries, dynamic flows, and nested influences. Our solar system is not an island, but a momentary eddy in a galactic stream, its edges shaped by forces older and larger than the Sun itself. And we, aboard a small blue planet riding this solar stream, have only just begun to perceive the magnitude of this architecture. The heliosphere is our vessel, our shield, our archive, our transmitter. Through it, we speak with the galaxy, and the galaxy, in turn, speaks through us. It is a dialogue not of language, but of plasma. Not of symbols, but of waves and fields. And though it began long before we arrived, we now listen, record, and interpret. We are the first generation to detect the whisper of the Sun's boundary, and to realize that what we hear is not an ending, but the opening of a cosmic continuum. And so the heliosphere, once thought to be a silent outer wall, reveals itself as an active membrane, a pulse of solar identity inscribed upon the fabric of the galaxy. It is a structure shaped not only by the fusion heart of our star, but by the larger forces flowing through the spiral arms of the Milky Way. It bends, breathes, filters, remembers. It defines the boundary between what is intimately ours and what belongs to the cosmos at large. In its charged winds, in its trembling edges, in its sprawling tail that fades into the galactic dusk, the heliosphere carries the essence of a singular star in conversation with infinity. It marks the point where solar physics becomes galactic astrophysics, where local becomes universal. And in tracing its shape, in measuring its fluctuations, in following its particles into the dark, we are not merely studying a phenomenon. We are listening to the breath of the sun, and through it, hearing the rhythm of the galaxy itself.